This is a graph of Bing query latencies in mid-February. For the purposes of this talk, we can dispense with the precise definitions for the red, green, and blue lines. All that matters is that the y-axis corresponds to the query processing time, and that on the night of the 13th, query times fell across the board as we cut over to a new search engine based on the BitFunnel algorithm. The graph is interesting from a business perspective because it says that with BitFunnel, we can process queries at half the cost, which is a big deal when you're running on thousands of servers. It's interesting from a technological perspective because BitFunnel is based on bit slice signatures, a once promising approach that fell out of favor in the late 90s. Prior to BitFunnel, signatures faced a slew of challenges that discouraged commercial adoption and dampened enthusiasm for research in the area. In the next 15 minutes, we will talk about these challenges and the approaches we used to build a competitive signature-based search engine. First, let's get up to speed on signatures. Suppose we have a very small document with just 3 terms. We can encode the set of terms in our document using a fixed-length bit vector, sometimes known as a document signature or a Bloom filter. To keep things manageable, I've chosen a very small vector with only 16 bits. But in practice, these vectors typically have about 1,500 bits in a web index like Bing. At this point, our vector is all zeros because it is the empty set. Let's add the term big. Our Bloom filter is configured with a number of hash functions that map term text to bit positions. In this example, I'm using 3 different hash functions to map the term big to 3 different bit positions. Adding big involves setting these 3 bits. Let's add another term. Early on, when the filter is almost empty, terms don't usually collide with each other, but eventually as the filter fills up, we see terms mapping to bits that have already been set. In this case, dog maps to position 3, which was set earlier when we added big. This overlapping of term bits is by design, but it does place a practical limit on the number of terms that can be added to a set for a given vector length and hash count. Now, testing membership involves probing each of the hash functions for set bits. Suppose I want to test for the word cat, which is not in the document. In this case, one of the 3 bits is a 0, so we know that cat cannot be a member of the set. When testing for big, all 3 of its hashes map to 1s, so we report it as a possible member. Why do I say possible? Well, consider the case of house. Its hashes all map to 1, so we report it as a possible match, even though house was never added to the set. How did this happen? Well, the term brown contributed 2 of the set bits, while dog contributed another. This is what we call a false positive. Bloom filters are conservative probabilistic data structures. This means they will always report membership for items in the set, but on occasion they may lie and report membership for items that were never added. So let's use Bloom filters to create an index. We'll start with a Bloom filter for the first document, document A, and then we add another for document B and C and D and so on until we've added every document in the corpus. The rows of this index encode the 16 documents A through P as 16-bit Bloom filters. Now a conjunctive query is represented as the signature of a small document that contains the terms of the query. A search involves a for loop over each of the documents. We're looking for documents whose signatures contain all of the bits that are set in the query. Document A cannot match because bits 2 and 9 are not set. Document B has bits 2, 5, and 9 set, so it is reported as a possible match. We continue iterating over the documents one by one, reporting matches as we see them. It's a very simple algorithm, but it's impractical because processing a query involves inspecting every single bit in the data structure. To see why, let's teleport back to the era of 8-bit microprocessors. To test document A, we need to check this bit and this bit. When we ask the 6502 processor to read either of these bits, it reads an entire byte. When we go to check bit 9, the same thing happens. In checking for 3 bits, we've managed to move the entire Bloom filter for document A across the processor's data bus. As we continue to check documents, we march across memory until we've read it all 48 kilobytes. Now you'd think things would be better today with the Xeon processor, but we see the same problem, just at a larger scale. In a web corpus, the filters tend to be about 1,500 bits wide, and we're typically checking about 6 bits per row. When we go to access a bit, our stick of DDR4 gives us back 512 of them. If we do 6 of these 512-bit reads from a 1,500-bit row, we're almost certainly going to read the entire row. So we have the same picture, but now to process a query, we're going to access, say, 120 gigabytes instead of 48 kilobytes. So what's a programmer to do? It turns out, around the time the Apple II was becoming popular, a fellow named Roberts realized you could eliminate a lot of the reads by rotating the bit vectors. With this arrangement, we only need to inspect the rows containing the bit positions in the query. In this example, we're looking at 3 rows out of 16, or about 1/5 of the total memory. In Bing, where we examine 6 out of 1,500 rows, this technique reduces memory access by a factor of 250. So to process a query, we extract the relevant rows, and we AND them together. The result is a vector of 1s and 0s where the positions of the 1s correspond to documents that are likely to match the query. This operation is fast because we can combine a machine word of bits in a single ALU operation, and there's no need for bit twiddling and masks. The algorithm is really clever and elegant, but it's still really slow. The reason is that the rows are really long, and we have to scan them in their entirety. Suppose we only had 1,000,000 documents. We'd need to scan 128 kilobytes for each of the 3 rows. That's nearly half a megabyte to process a single query. It hardly seems fair. An index based on posting lists can just skip over all of the documents not on the list. But we have to look at each and every bit position. Or do we? This brings us to the first BitFunnel innovation, and we call it higher rank rows. A higher rank row is just a shorter, lower resolution version of a row. It can be scanned more quickly, but the catch is it creates more false positives. Let's take a look. Here's a row with 32 bits, each of which corresponds to a single document. We call this a rank 0 row. We can construct a higher rank version by taking the left half and the right half and ORing them together to produce a rank 1 row with 16 bits. In this new shorter row, each bit position corresponds to 2 documents. We can continue in the same fashion, splitting the row and then merging its halves, yielding a rank 2 row where each bit corresponds to 4 documents. We continue this process through additional iterations, losing information while producing ever shorter rows. The shorter rows can be scanned quickly because they have fewer bits, but they introduce more false positives because each bit is less definitive. Now let's take a look at how we use higher rank rows. Suppose we're searching for a term and we use our 3 hash functions to isolate 3 rows. With normal rows, we'd just intersect them and be done, but then we'd have to scan each row in its entirety. We can reduce the scanning time by creating higher rank rows when we build the index. For example, we might combine the 4 parts of row 2 and store a quarter-length row. Or we might combine the 2 halves of row 1 and store a half-length row. With this index, each of the hash functions would map to a row that could be full-length, half-length, or quarter-length. Finding matches now involves intersecting rows with different lengths. But what does this even mean? How do we intersect rows when they don't have the same number of bits? Well, conceptually, what we're doing is intersecting an expanded version of each of the rows. With row 2, for example, each bit corresponds to 4 documents, so its expanded version is just 4 copies of the short row. In row 1, each bit corresponds to 2 documents, so its expanded version is just 2 copies. Now we could just expand each of the rows at query time and intersect them like before, but we'd lose the speed benefit while still increasing our false positive rate. It turns out that with careful use of intermediate results, BitFunnel can perform this intersection directly on the shorter rows, making the running time proportional to row length. Here's how it works. We left align all of the rows and then intersect the portions they have in common. Now we just intersected 3 bytes, but we can reuse the intersection of the first 2 bytes by shifting to a new alignment and intersecting again. Then we start over at another position. We intersect 3 rows, and then we reuse the intermediate result at a different alignment. In this way, we produce a complete result vector without ever expanding the shorter rows. Higher rank rows speed up searching, but we're still leaving money on the table because traditional Bloom filters waste space when used to represent terms with a Zipf-ian frequency distribution. BitFunnel uses frequency-conscious Bloom filters to reduce memory consumption. Consider this Bloom filter which has a 10% bit density. I'm depicting it here as a row, but it actually corresponds to a column in the rotated bit-sliced index. Suppose we're looking for a term that's not in the filter. What is the probability that the filter will report a match? It all depends on the number of hashes. With a single hash, we have a 10% chance of hitting a 1. With 2 probes, we'll report a false match 1 time in 100. The odds of a full house drop geometrically as hash functions are added. For this talk, I'm going to express false positive rates in terms of a signal-to-noise ratio. The signal corresponds to the expected number of true matches, while the noise corresponds to the expected number of false matches. If we're looking for a term with frequency f, the probability of reporting a false positive is the product of 1 minus f, the probability that the term is not in the set, and density raised to the k, which is the probability of probing all ones. We'll call this probability the noise. The signal is just f, the frequency of the term in the corpus. Let's use this expression to compute the signal-to-noise ratio for a number of terms, some common and some rare. Consider the word with, which appears in half of all documents in our test corpus. In a Bloom filter with 10% bit density, a single hash yields a signal-to-noise ratio of 10.2. This means that we will report about 10 true matches for every false positive. The term info is 5 times more rare, and it requires 2 hashes to maintain a similar signal-to-noise ratio. Movies, which appears once in 100 documents, requires 3 hashes, and so forth. The headline here is that rarer terms need more hashes to drive down the false positive rate. This example only goes out to Sawmill, but the internet is full of extremely rare terms that may require 10 or more hashes to reach an acceptable false positive rate. Things like GUIDs and DNA sequences. To find these rare terms, a traditional Bloom filter would need to be configured with lots of hashes that would waste space for the common terms. BitFunnel uses term frequency to set the number of hashes on a term-by-term basis. So we've seen how higher rank rows can reduce scanning time for rarer terms. We've also seen that rarer terms require more hash functions or rows to drive down the false positive rate. BitFunnel combines these two concepts to define a treatment for each term. The treatment is just the number of rows associated with the term at each rank. So, for example, a common term like with might map to a single long row, while info with an IDF of 1 might map to a pair of rows, one full length and the other half length. As terms become rarer, they are assigned more rows, some of which are dramatically shorter. Now you might wonder whether there's a simple pattern behind these term treatments, and I don't know the answer. We used a brute force optimization to sort through treatments yielding a certain signal-to-noise ratio while managing a trade-off between query time and memory consumption. It turns out there are about 1 billion distinct treatments, and we just evaluate each one at each IDF value. This takes a couple of seconds and is performed once during system configuration. So let's try a simple query. Suppose we're looking for treacherous movies. BitFunnel maintains a mapping from each term to its treatment. The treatment tells us the number of hashes to use at each rank, and this gives us the rows, which we isolate, interleave, and then intersect to get the match set. Now this slide gets at the essence of why BitFunnel is fast. Let's focus in on the first 4 rows. Suppose these rows have a 10% bit density. When we intersect the first 2 rows, the ones in the result vector will be about 100 bits apart. This spacing already exceeds the 64-bit width of the accumulator, so at every other quad word, if we don't see a match, we're seeing a register full of zeros. When this happens, we bail out because we know that further row intersections cannot find matches. Now after intersecting 3 rows, the ones are 1,000 bits apart, so if we don't see a match, we're skipping every other cache line. By the time we get to 4 rows, the ones are 10,000 bits apart, about 20 cache lines. At this point, we rarely access cache lines in the gray rows unless there's a match. So evaluating the query involves reading the first 4 rows in their entirety, and then another 8 cache lines per match. We just saw how frequency-conscious Bloom filters allow us to save memory in the face of widely varying term frequency. We face a similar one-size-fits-all challenge when the corpus has documents with widely varying lengths. This index has a fairly uniform distribution of bits, but if some of the documents were extremely short, we would end up with sparse columns that waste memory. And long documents would overfill columns, leading to excess false positives. In BitFunnel, we shard the corpus by document length. I'm breaking it into 3 parts here, but in Bing we actually split it 10 or 15 ways. Once the columns are grouped by length, we can customize the number of rows in each shard to conserve memory and control the false positive rate. Let's see how this plays out with our earlier example. Recall that we started with a query that involved the intersection of 3 rows. We then split our index into 3 parts. Now evaluating our query involves 9 rows. This idea of sharding by length was proposed in the 90s, but it was considered unacceptable at the time. To see why, let me set the stage. This is Google in the mid-90s. At the time, the world's leading search engine ran on a handful of machines, and research focused on single machine solutions where the index resided on disk and seek times dominated. Before sharding, we did 1 seek per row. Sharding turned this into 3 seeks per row. On a single machine with a single spindle, this was a deal breaker. And remember, in the real world, it's even worse because we'd need to shard 10 or 15 ways to handle the dynamic range of documents on the internet. Now, fast forward to the present day. Our index doesn't fit on a server. In fact, it is spread across thousands of servers. We're already sharding the index across machines, so it costs us nothing to use document length as our organizing principle. In our large cluster, even with length sharding, each server does only one seek per row. Another difference from the 90s is the use of RAM. It is commonly believed that RAM is more expensive than disk. Here I'm comparing a $50 hard drive with 2 sticks of DDR4. The 1 terabyte drive clocks in at a very economical 5 cents per gigabyte. The DDR, on the other hand, costs $7 and change. Ouch! The problem with this analysis is that dollars per gigabyte is the wrong metric for search. Let me explain. When you are running a commercial search engine, you have a business need to process queries at some rate Q while searching a corpus of D documents. Your costs are proportional to the area of the DQ box. One way to meet the demand would be to shard the corpus across 4 fast machines, each of which can process Q queries per second. Queries would be broadcast to all 4 machines and the results combined. If, on the other hand, you had a slow machine that was capable of storing the entire index, you might replicate it to achieve the desired throughput. In this case, a load balancer would distribute queries round-robin to the 3 machines. When we model BitFunnel on a storage device, the number of documents D is proportional to the device's capacity. To process a query, the BitFunnel algorithm scans some percentage of storage. This percentage is independent of the actual capacity. If a typical query scans 1% of a megabyte index, the same query will scan 1% of a gigabyte index that holds 1,000 times as many documents. Therefore, the rate at which queries can be processed is proportional to the device bandwidth over its capacity. The product of D and Q, the area of the box, is then proportional to the bandwidth. For BitFunnel, device bandwidth is a proxy for serving capacity. When we consider serving capacity, RAM is much cheaper. 2 sticks of DDR4 provide the serving capacity of 179 hard drives, and $1 of DDR4 is equivalent to $76 of disk. The only catch is that your business must be able to utilize the extremely high throughput that RAM offers. In the 90s, there just weren't enough people using search to justify RAM. Today, commercial search engines have sufficient load to consume most of the bandwidth in a stick of DDR4. Let's talk about false positives. Signatures generate them and posting lists don't. One criticism of signatures is that the cost of verifying all of the proposed matches is prohibitive. This is a valid concern when you're implementing a database and want the result set in its entirety. It's not an issue in web search, and let me explain why. The goal of web search is not to find all of the documents containing a certain set of keywords. Rather, it is to delight the user by returning those documents that best match the intent of the query. In Bing, we have a ranking oracle that takes a document and a query and generates a score indicating the document's relevance to the user's intent. It's a complex system that considers thousands of signals, and to some extent we don't even know how it works, because it's based on machine learning over a high-dimensional space. It is also really expensive to run. If we had unlimited time and resources, we could simply submit the entire internet to the ranking oracle and return the 10 most relevant documents. Fortunately, we can do better. In Bellevue, Washington, there is a building with about 1,000 engineers, and on any given day, a bunch of these engineers are inventing new ways to avoid sending documents to the oracle. The main technique in their playbook is to filter out those documents whose terms fail to match a Boolean expression. Before BitFunnel, this was done with an inverted index of posting lists. BitFunnel runs much faster than the inverted index, but it also generates false positives that are passed on to the ranking oracle. BitFunnel wins because the time to rank the false positives is smaller than the time saved in the filtering stage. BitFunnel has powered Bing's super fresh news index for the past 5 years, and we know without a doubt that it is faster and more economical than the proprietary system it replaced. We were interested in seeing how BitFunnel stacked up against top open source algorithms like Partitioned Elias-Fano, which I will refer to as PEF, and systems like MG4J and Lucene. Our experiment used the Gov2 corpus with about 100,000 Trek efficiency topic queries. It would be great if these sorts of bake-offs could produce definitive results, but in practice this is hard because it requires controlling for factors other than the algorithm. For example, we know that the implementation language can have a significant impact on running time, And we saw this in our experiment where the Java version of PEF was consistently slower than the C++ version. Now we can control for language by limiting our comparison to the C++ version of PEF, but we'd still see differences because PEF doesn't parse queries, while BitFunnel uses a general-purpose pipeline that handles arbitrary Boolean expressions. Another challenge is that BitFunnel's planner compiles each query into native x64 code. PEF doesn't pay for an analogous compilation step, but it also doesn't benefit from the native code. Who's to say how query compilation impacted the results? The bottom line is that running time is impacted by the planning algorithm, the rate at which the corpus can be scanned, and the cost of handling matches. Unless you control for all of these factors, your findings are likely to be considered anecdotal. So with that caveat, let's look at our results. I'm only presenting the comparison with Partitioned Elias-Fano here because MG4J and Lucene were slower in every case. Since BitFunnel shards by length, the results here are broken out by shard. It was no surprise that BitFunnel ran faster, and oftentimes significantly faster than PEF. But here's the catch. The speedup came with some false positives and significantly higher memory usage. In the first shard, BitFunnel uses 5 times the memory of PEF. When we look at the cost of serving, which accounts for the trade-off between speed and space, we see that BitFunnel outperformed PEF on shards with longer documents, while PEF won on shards with shorter documents. Our experiment looked at individual shards, but if we combine the results mathematically, we see that BitFunnel is competitive with PEF. In the late 90s, it appeared that signatures were a dead end. Today we have ample evidence that signatures can provide a dramatic cost savings in a large commercial search engine, and our apples-to-apples comparison with PEF shows that signatures are contenders worthy of further consideration and research. Our experience with Bing suggests that the production version of BitFunnel is likely to outperform PEF, but even if it has the same costs as PEF, it is still a better choice because it allows for lightweight, lock-free incremental index updates while processing queries. For more information, visit our project site at bitfunnel.org or browse our code on GitHub.